yeah, I'll be telling you about joint work with all of the people on here as well on this Axiom Profiler, which is a tool that will help you debug issues like when you're using SMT solvers. And if you run into performance issues, then hopefully you can use this tool to help debug those issues. And I mean, I imagine most of you understand kind of why we're looking at SMT solvers, but to kind of for the others, essentially, pretty much all verifiers that we have in Rust, especially like the ones that are automated, where we just click verify and it runs and says yes or no. So everything like Varus, Crusoe, Prousty, and so on and so on. All of these tools will use an SMT solver in the backend. So they'll do some translation where they take the Rust program with annotations and create an SMT file that they give to an SMT solver such as E3. And then this SMT solver will return some yes or no answer, sometimes also a timeout or unknown. And within this query to an SMT solver, the most common cause of performance issues is generally when there are quantifiers that are used. And so this, to a user, sometimes users also write quantifiers in SMT solver or in verifiers. Sorry, so if I'm a user who wants to write that an array is sorted, then I'll generally use a quantifier for this. But there are also many more quantifiers kind of under the hood that are used within the verifier itself, that it adds to whatever encoding to reason about all of the built-in types and all of the built-in stuff that the verifier has. And so, yeah, all of these quantifiers that we use when in verification, they cause a lot of issues. And the tool here, it will hopefully help us kind of figure out where those issues are, because this is generally quite non-trivial. So a quantifier that someone's written, it might look harmless, but it actually is causing a severe kind of performance degradation. And here I've listed a few kind of papers and other work of people trying to get this right and describing the process and describing how to kind of write good quantifiers and good triggers. And so in this talk, I'll kind of demonstrate the tool, but I won't exactly explain how to write quantifiers well. So also I've listed these here as a reference so that you can kind of take a look at those if you're interested in more detail. Okay, so now that we kind of know how verifiers use quantifiers in SMT solvers, let's actually see it in an example. So an example like this, where I've written it as a Rust file, but this is kind of meant to be somewhat general to whatever verifier of some arbitrary programming language. And I've taken a very kind of simplified toy example just to demonstrate the common issues that one might run into. So don't treat this as a full Rust verifier. And so the example that we have here is we have three different functions that we somehow want to reason about. We have a slot function, which takes a slice and an index into a slice and returns the address of that index in the slice. Then we have a lookup function, which will dereference our address and find the value which is stored at this address. And we have a next function, which does kind of pointer arithmetic. So it takes an address and offsets it by 1 to get the next address. And so this already gives us some stuff that we might want to reason about. And here we're kind of in the context where we don't have some smart Rust verifier, which is already encoded what all of these Rust operators do. We actually want to kind of tell, we're working here at a very low level and we want to tell the SMT solver how these functions work. And so the way we'll do that is to write some axioms about them. So I have written that in some sort of pseudocode where these axioms, they're essentially quantifiers. So for instance, one axiom that we might want to have is that this slot function where we're taking the address in our slice at index I, we want to say that this function is injective. Namely that if we take two indices which are not the same, and we take the slot, so the address at those two indices, then those two addresses will also differ. So this way we've encoded the injectivity of slot. Then we have another axiom where we're kind of relating this next function, which does our pointer arithmetic, with indexing into the slice. And so we're saying if we index the slice at index I, take the address there, and then take the next address, then that's the same as if we just directly indexed at I plus 1. So we're relating kind of this integer arithmetic with address arithmetic. So we have this one. And then I also have written here this trigger annotation. We'll get to that a bit later. So this tells the SMT solver how to use this quantifier. And then lastly, I've kind of written some client code here to demonstrate how we might use those functions that we have above, where the client code gets a slice, an index into that slice, and then some length, which corresponds to the length of the slice. And I've written here some assumption. You can imagine this is a precondition or something where we're saying exactly that this slice is sorted. So for any indices between 0 and length, if we take a look at the index, so we index into the slice at index I, and we get the value, so we use this lookup function, we get the value there, then this value will be smaller than or equal to if we were to look up the value at the next slot. And here, then lastly, I've written some kind of assertions that maybe the verifier would want to check. These are actually not super important. They're just some initial state for the, there's some initial state for the for Z3 to start working with. We'll see. I mean, if you take a look at it here, you can see that this actually shouldn't hold because we're asserting that if we look up here, then it's going to be strictly less than if we were to look up the next slot. Whereas our sortedness thing is giving us less than or equal to. But the point of this is that we kind of don't want Z3 to terminate quickly and to be able to prove or disprove something quickly. We want it to run for a bit so that we can then analyze the behavior. And so now we have our example. And essentially what a Rust verification tool would do now is to take this and turn it into an SMT file. So I won't explain this file in too much detail, but this is essentially what would go into the SMT solver, into Z3, where we've declared our kind of slice and address encoding that corresponds to those two. We've declared functions for the three functions that we had. And additionally, you might notice here, I've also included some kind of heap where we carry around a heap, and this lookup not only takes an address, but also takes a heap to dereference that address in this current heap. But the most important part is that we've copied over all of our quantifiers that we had. So here we have our injectivity quantifier. Then we also have this next definition quantifier. And then lastly, here we also have the sortedness one. And now one more thing we want to notice here is that we have this pattern annotation within the SMT2 file. So that corresponds to the trigger annotations that I had in the Rust file, where, for instance, here we've specified this slot slice I pattern, and this tells Z3 how to use this quantifier. So I'll switch now back to the slides to kind of explain this. It's a bit easier on the slides than here in the code. But essentially, let's take a look at this in the context of these two quantifiers, this next def and the sortedness, where we have these triggers. So we have this slot slice I that Z3 will be matching. And then we have this lookup heap slot S I pattern. And so when Z3 gets a quantifier like this, the behavior of how it uses that quantifier is very much entirely determined by this trigger. And so once Z3 gets a quantifier like this, it will ignore most of it except for the trigger. So it will essentially take these two quantifiers and turn them into patterns that it tries to match against things that it sees. So it takes the two quantified variables here and just leaves them as wildcards and uses the rest of it as a pattern to look for things. And so then now that it's kind of interned these quantifiers, it will start looking at other terms that it has. So we had this assertion at the end of our program where we asserted that looking up in the heap at next slot something will be greater than some other thing. But this is just some constant that we're giving to Z3. And so it will, we call these ground terms, and it will take this ground term and just put it in some list, some data structure that it uses to hold all of the ground terms that it's seen so far. And not only does it add this full expression, it will also just take all of the sub-expressions of that and add those as well. So it takes this lookup, then the next function application and the slot. And then now comes kind of the key part of how it handles quantifiers. And so here, once it has collected all of the ground terms it can see in the context, it will try and take one by one all of these ground terms and compare them to the patterns it has for the quantifiers. And so this is this process called e-matching. And that's how SMT solvers handle quantifiers in relation to verification tools. And so the matching part corresponds to matching this these terms, and the E stands for equality. So it's matching them modulo quality, and we'll get to that in a bit. But we can now already see that here we have a match, right? So we have a term slot with some arguments, and we're trying to match against a slot function application. And so Z3 will notice this, and it will kind of take the quantifier and it will instantiate it. Namely, it will take the two arguments that it sees in the ground term that it has and substitute those for the quantified variables. And if we do that, then we get this. So this is the body of the quantifier that we had with those variables substituted in. And now the process repeats. So this is a new term that we know to hold within the SMT solver. It adds this to the list of ground terms it has, and it also adds all of the subterms. And so this is how the SMT solver will handle quantifiers. And we can take our file that we have here and actually run Z3 on this. So the command I'm using here is Z3. And importantly, for the Axiom Profiler, we want to pass these two flags, which instructs Z3 to create a log file that then we can analyze. I'll also use a timeout of 1 second, just so that this log file doesn't get too big. But yeah, here it could run for longer. And I'll point it to the file that we have here. So now when I run Z3 on this, let me check that and change anything. Yeah. Well, we get a timeout because it couldn't solve things in 1 second, but we don't care about this too much right now. We're kind of trying to figure out, are there any issues with the quantifiers that we have? And so we ran Z3, and what happens is that Z3 produces this log file. If we open it, it's just lots of lines of Z3 logging what it's doing step by step. And this log file is generally really quite big. So there's no way we could kind of go through it manually and figure out what's happening. And this is exactly where our Axiom Profiler comes in. So if I open the Axiom Profiler here, this is the repository of the Axiom Profiler. And the tool is written in Rust and it's compiled to WebAssembly. So that means that we can just click this link and it runs in the browser. And I'll switch here to the nightly version so that we get all of the latest features. And then I can open this directory where Z3 created the log file and open this log file in the Axiom Profiler. And now we can see the UI of how we can explore the instantiations from this run of Z3. On the side, we have different options on how to kind of show this graph that we have here. Some of the options here, they're kind of hiding or showing nodes. So for now, I'll show all of the nodes so that we can explain what's happening. So I enabled the nodes here, and I'll also increase the number of nodes shown. So if I press the edit, and I change this to 310, then it's going to show 310 nodes. And what we have here is a kind of filtering operation. So the graph that we're displaying for instantiations is not going to be the full graph because there's going to be way too many instantiations for us to kind of make sense of. So the tool by default, it shows only the top 300. And within the tool, we have a metric for determining some kind of estimate of how expensive an instantiation was. So we're showing only the most expensive ones. And now we can look at this graph here. So if we relate back to the slides that I was showing, maybe I'll zoom in a bit so that the text is visible. If we think back to the slides that I was showing just a moment ago, then here we can see that we have this kind of ground term that I was showing, this slot S of index. And this ground term matches the trigger. And this node here now represents that instantiation of the quantifier. So the gray nodes represent the ground terms that Z3 has in its context, and the colored node represents instantiations of quantifiers. And the different colors represent the different quantifiers. So this green one here is representing this next def. The yellow one, it's representing sortedness. But now, if I click on one of these nodes, we get the information about the instantiation on the side here. So let's go through that to see what the tool is showing us here. Well, it tells us what quantifier and what the body of the quantifier is. So this is our next definition quantifier that we had. And here it's also telling us how exactly it was instantiated. So it's saying we have this trigger, and that trigger matched against this ground term, where the slice quantified variable is instantiated with S, and the I quantified variable is instantiated with index. And if we do this substitution, then this is the resulting body of the quantifier. So now this is the new term that Z3 introduces into the context. And here we also see which of those subterms from this term are actually new, so that they're newly introduced. We can see, as we saw in the slide, we already had a next slot S index in the context. So this subterm, for instance, doesn't appear here. Okay, so this is all of the information that we can see in the graph, and it's kind of organized this as a graph where we show the dependencies. So this term here caused the instantiation, so we have an edge between the two. And now let's take a look at what the tool can do to help us identify issues with this log file. So probably the most useful button here on the side is this view matching loops button. So if I press that, it analyzes the file, and it tells us that it found two potential matching loops. So these matching loops are kind of repeating instantiations, which will severely degrade the performance. And we can click through them. If I click the first one, that's a bit more complicated. So let's take a look at the second one first. And this second one here, yeah, we can see this long chain. I can scroll down and we can see, yeah, it goes for really quite a while. We can see this long chain of repeatedly this green quantifier being instantiated. So we can click through it a bit to try and understand the issue. Where here we've already walked through this instantiation, and the key ground term that is being produced that we need to take a look at is this slot S1 plus index. So I can click on it. We can see this is that term. And you might already now notice what the issue is that this slot S1 plus index is a new term, and this new term again matches the trigger that we had. So we have our trigger for this quantifier, and that again matches it. So it will create a new instantiation, and that new instantiation again creates some new terms in our context. And one of those new terms, if I click here, is this slot S2 plus index. And so that again will cause another instantiation, and then this just keeps repeating forever. I mean, there will be some limit in Z3, so it might go 100 times or something, but it's still going to severely affect performance. And additionally to that, the tool here, it also tries to kind of explain this repeating pattern. So it takes this chain and tries to generalize the terms that it sees. So here it has this next def quantifier, and it's saying that we're repeatedly matching this trigger, and we're repeatedly creating terms with slot S, some number plus index. And so this visualization, it's still a bit of a kind of new feature, so it's still a bit of a work in progress. But you can kind of clearly see that there is a loop here where we're repeatedly instantiating, creating a new term, and then instantiating again. So now the tool has helped us kind of identify this issue. So let's see how we can fix it. This is one thing that the tool won't really help us with. You need to take a look at, for instance, the papers that I linked to, and how they describe kind of how to write, how to improve these different situations. But I mean, here we've kind of identified this chain, and we've identified that this is an issue with a single quantifier, right? So in our file, we have the 3 different quantifiers, but clearly here it's just this green one, this next def. So if I switch back to the file and we find that quantifier, this next def one, then we can see our definition here. And the first thing that I generally would try when trying to resolve these issues is to try and change the trigger that we have. So the trigger that we're matching against currently is this slot slice I. And often an issue we might have is that this trigger ends up being a bit too lenient, in that we're matching against too many things. And one thing that we can try to do instead of matching against this subterm is to take the whole subterm here with this next as well. And if we add the next to the pattern like this, then now it will still trigger if we see a next of slot of something, but it won't trigger on this slot slice I+1, because the right-hand side here doesn't have a next anymore. And so now let me run Z3 again. We'll regenerate the log file, drag it here and open it. Now, if I zoom out a bit, we can see that the graph is a bit chaotic. So generally, in these situations, we want to reduce the number of nodes that are displayed because we can't make sense of such a chaotic graph. So maybe I'll decrease it to, say, 100 nodes. And additionally, I'll hide some of these extra nodes. So before I was showing them to kind of explain the full picture, but now we mostly just care about the instantiation. So I've hidden the gray nodes, which are, for instance, the ground terms that appear. And now, again, we can see that we've removed these edges between the green nodes. So that's now been fixed. You can see our new trigger here. But there is still a repeating pattern here. So we'll get to that in a bit. But now let's first take a look at another very useful feature of the tool, which is this hide all but high degree nodes. And what this does, if I click it and say, for instance, show only 10 nodes with a high degree, what it does is it will figure out the nodes which have the most children. That means that they've caused the most instantiations, and show only those. So here we have these green ones. If I click on one of them, we also get some filtering operations which are specific to that node. And the one we care about here is to show those children. So this one is causing lots of children, lots of instantiations. And if I click this button, it will show all of those. I'll zoom out a bit. And here, yeah, we can indeed see that this instantiation is resulting in lots and lots of other instantiations down here. We can click on one of these and see that this is our injectivity quantifier. And so what's going on here? Well, let me make this a bit bigger. What's happening is that the pattern for injectivity is saying to Z3, if you ever see a slot slice of something and a slot slice of something else, so this I and J, then instantiate the quantifier. But the problem is that we're creating in our loop that we had, we're creating lots of slot with some index +1, index +2, and so on and so on. And you can kind of notice here, yeah, we're matching this slot 2+ index and 3+ index. And the problem here is that this ends up being quadratic in the number of these slot terms that we have, right? We kind of take any two pairs of those terms and we'll have an instantiation for it. And so then if we end up having lots of these terms, it's going to result in really quite poor performance. And now to fix this, again, the tool will help us identify it with this useful filter, but it's not going to tell us how to fix this. So we'll need to refer to the papers that I linked. But this is, again, let me switch back to our file here. This is, again, a common issue that comes up. So there's lots of people who have described how to fix this. And the issue here is that the issue is with our pattern, but it can't easily be fixed by changing it here. So the way to fix this is that we'll have to notice that there's another way to express injectivity, which is to say that there exists some inverse function. So this existence of an inverse function will also let us prove that the slot function itself is injective. And I'll copy this over from this file that I have pre-prepared so I don't mess things up. But we can take a look here. The delta is that I've created a new slot function, which essentially in Rust would correspond to taking a slice and the address produced by our slot function and returning us the index that was passed in to the slot. So this is this inverse. And now I've redefined this injectivity quantifier to say that the two functions are actually in inverse. So if I take any slice and index I, then if I take the slot at index I and I do slot inverse on it, then that's again going to return to like it will be equal to this index I that I passed in initially. And this is also including injectivity. So it's giving us the same property that we wanted, but we've slightly had to change the quantifier. And so with this new version, let me save it and rerun Z3. Now with this new version here, if we open this, and let me disable the extra nodes again, like I did last time. So we just have our instantiations. If I now click show only the 10 most with the highest degree, we have these nodes, but we can see if I press show children, then all of these nodes only have 2 children now. So each green instantiation results only 1 instantiation of our injectivity axiom. Because this injectivity axiom is matching this single trigger like so. Okay, so now we've resolved another issue within the file, but actually there is a third issue. I mean, we can see that a bit if I reset the filters back to the original one. We can still see that we have a long chain like this. So that's one last issue in the file. I can again click this view matching loops button in the tool, press this next to find that one matching loop. If I make it bigger, then here we can see a visualization of that matching loop. And this one now, it's a bit more complicated in that they're not directly matching on the term. So if I click on this instantiation here, it's producing, hide this. So it's producing a term like this where we have, that's our sortedness is producing a lookup heap next slot S and so on. And if we take a look at the next instantiation in the chain, then what's being matched is this trigger. So essentially, the previous yellow instantiation created this term, but this term doesn't immediately match the trigger, but instead we need to use an equality to rewrite things. So let me actually switch back to the slides to explain that in detail, because again, it's hard to see there. So what we just did first, well, we noticed that we had this matching loop where we're repeatedly matching the slot, right, with index plus 1, index plus 2, and so on. So we changed the trigger, and now this trigger only matches this ground term, but then there are no more ground terms later on that would match that trigger. And then we change it, we changed our injectivity, but that's not here. And now what we're taking a look at is this repeated instantiation of the sortedness quantifier. And so what's happening is that we have our lookup term in the list of ground terms, but this term doesn't match the pattern that we have, right? We have this extra next function application that doesn't appear in the pattern. But earlier we got an equality asserted that this next is equal to slot S index plus 1. And so when Z3 gets such an equality, it will remember it somewhere internally, and it will be able to use these equalities to rewrite our term. So it takes this term, takes the next slot S with the left-hand side of the equality and rewrites it to the right-hand side. So it produces a term like this, where we have slot S index plus 1. And now this new term that was rewritten with the equality, now that does match our trigger here, where we're substituting I for index plus 1. And so we can indeed see this, where if I click on this first one, this is exactly what was there on the slides, where we have our lookup next something term, which wouldn't immediately match the trigger, but we're able to use this equality to rewrite the term to one that does match. And again, the tool now displays all of the other information afterwards. And so the issue here, I can switch back to our SMT file. It involves this sortedness quantifier and the next definition quantifier, which is this one. And here the fix that we'll use actually is to slightly change the sortedness. So this is very often in verification, we don't want to express sortedness in this way, where we're talking about adjacent elements, where we're talking about I and I plus 1, but actually we want to use two arbitrary indices, why one is less than the other, and say that those two will be transitively kind of less than or equal to one to the other. And so I can copy over the solution so that I don't have to type it out. And so yeah, here what I've changed is I'm quantifying over two variables. I'm saying those, maybe this version is easier to look at. I'm saying those two are within the bounds of the slice, and one is less than the other. Then if we look at the value within the slice, then also it's less than or equal to the other. And so then if we take this last version, we run Z3 on that, and we find the log file that was produced. Now it's way simpler. So if we take a look here on the left, we're filtering to show the 300 most expensive, but actually there aren't even 300 instantiations. We only have 56, or if I actually only show the instantiations. So we only have 50 instantiations. And so we've really drastically reduced kind of the number of instantiations that Z3 has to do. And this will improve the performance, where I kind of showed the one example client code, but for whatever client code we might have, it will generally improve the performance of verification by orders of magnitude here. And we were able to use the Axiom Profiler tool to actually figure out where the problem, which of the quantifiers are the problematic ones, and kind of where the issue is. But then the tool isn't able to go all of the way. It's not able to tell us how to fix this. So now we saw the demo and we kind of saw the current state of the tool. Well, the tool is building on top of a previous tool that already existed for debugging quantifiers in the same way. So it's essentially, we're kind of developing the tool to try and be a general purpose debugging tool for most SMT related things. But to start with, we essentially took the old tool, took all of the features that it has, and re-implemented those in this new one, because the old one had quite a few issues. It only ran on some older version of Windows. It would often crash. It would be pretty slow, and so on. So now this new tool written in Rust, it's able to do things a lot faster and not crash. And it's able to do pretty much all of the stuff that the old tool could do, in some places even more. And so generally now I would recommend using this new tool instead of the old one. It also supports a lot more Z3 versions. So currently the only SMT solver that we support is Z3, but it supports roughly the past 5 years of Z3 versions. We're hoping that at some point in the future, we can kind of extend this support to also work with, for instance, CVC5 and other SMT solvers. But right now Z3 is the most common, so that's one that we work with. And essentially the takeaway message is that this is already a very useful tool for people who are building verification tools. So for people who have to write axioms and kind of do the encoding into SMT files themselves directly. So, but there are also some next steps that we definitely want to take a look at with the tool. So one of these next steps is to actually make the tool really just as useful for users of the verifiers. So if I'm some user writing my Rust code using some Rust verifier, and I'm writing quantifiers within my Rust file as specifications, then I might also run into similar matching loop issues, similar performance issues with my quantifiers that I've written, and I want to be able to debug those. So to highlight that and what the current experience with such a thing would be, I've also written, or I took an example from Varus. So here we have some normal Rust code with some Varus annotations. And I took the example from the Varus guide on what a matching loop looks like. So here we have app. If I show this like so, then here we have some quantifiers in a precondition, and we have one really quite problematic quantifier. Hopefully you see it from what we've talked about, is that we have a quantifier where we've specified our trigger just matches whenever we see an f of some x and some y. But then when that quantifier matches and creates an instantiation, then we're actually creating new terms which will be larger than the one that we got in. So if we got in some 0 and 0 or something, then here now we're creating 0 plus 1 and 2 times 0 as new terms. And those again would match the trigger. So here, this is a really quite a problematic matching loop where we're creating lots of new terms that will again re-trigger the same quantifier. And what we can do here is run Varus on this. Varus has some mode where it actually will output the log file, so it will instruct Z3 to create the log file that we've seen. And it even has built in a bit of a similar analysis to our tool. So it's a command line version of this. So what I can do is I'll run I'll run Varus. I actually also ran it with a timeout of 1 second. And you need to run it with these command line flags to actually get that log file. And when I run it on this file, we see this built-in Varus analysis tells us that this quantifier was instantiated quite a few times. So we have an analysis like this, but we can also directly take this into our Axiom Profiler tool. So Varus will create this hidden directory with this profile file. And if we open that in the Axiom Profiler, we get another graph like this. So a graph similar to the ones we've seen. And I won't actually click through and explain this, but we have our blue quantifier, which corresponds to this quantifier that we saw this problematic one with the matching loop. And we can see these long chains of repeated instantiations. We could also click our view matching loops button to analyze the file, and then it will actually find lots of long chains of repeating patterns. But the issue currently, so we can already, as a user, if you saw this talk, for instance, you could probably already use this tool and try and identify some patterns in your code. But the problem is that it's not really natively supported. So when Varus takes your Rust code and translates it into SMT, it will add lots of its own stuff. So it adds some kind of polymorphism encoding where it's talking about the types of this X and Y. It will change the names of the functions. So we have our F function that we saw, this F function that we saw in Rust, while it now has a different name, and it adds different conversions. So this, for instance, I is going to and from the polymorphic version, the polymorphic type. And so it's just, the issue mostly is that it's hard to navigate. And so this is one future direction that we want to take a look at with the tool, is that for front-end verifiers, that they would actually provide not only the log file from the SMT run, but also some configuration file, which tells the Axiom Profiler how to handle these log files. And namely, the most important features that such a log file, such a configuration file would let the Axiom Profiler do would be to categorize the different quantifiers that it sees. So for instance, if we had some sortedness quantifier that the user wrote within Rust, then we could categorize that as a user level quantifier. Whereas if we had the verifier adding some injectivity axioms that the user, the user has never seen those quantifiers, it's just the verification tool itself adding those directly into the SMT file, then those could be categorized as verifier quantifiers and hidden from the user. So these injectivity axioms, as we saw, they can have issues, but that's up to the verification tool developers to fix those issues. And hopefully once they're fixed and the verifier is being used in the wild, then the user they can't change them. They don't really understand what these quantifiers are that the verifier is adding. And so we might want to filter those out within the tool and only show the ones that are relevant to the user. So by categorizing them, we would be able to have this functionality. And we would also like to have some functionality where the verifier is able to provide some formatting instructions. So within the SMT files, everything is just a function call, and it looks like this. But we might, for instance, for Rust, we might want to format things to look a bit more like this, where it's actually doing some indexing and maybe taking a reference or something. So that's one direction we want to take a look at. Another direction is to actually take this matching loop feature and improve it, iterate it a bit more. So we saw the graph that's displayed where it tries to generalize the terms. I think this could be improved a bit more to kind of actually make it more clear where the repeating pattern is, and maybe also to add some textual explanation of what is happening step by step within one iteration of the matching loop. So that's one thing. A second mode would be, I think it would be nice to kind of have some, I don't want to use the GUI, I don't want to actually have to click through things, but just I give you a log file and analyze it for me and tell me what the issues might be. So this is very similar to what we saw that Varus actually does on its own, where in the command line, it would actually display some stats about the log file. While here, ideally, we would have some actually even extra information within that to say, okay, we found some potential matching loops. Maybe there are some quantifiers that result in having lots of children and so on. So kind of one-click textual explanation of the issues or potential issues within the log file. And lastly, there's also some work now on kind of providing some formal semantics for e-matching and this kind of instantiation within SMT solvers. And so the tool could build on this and kind of try and actually prove or show that what we have here within the log file is actually a matching loop. So currently, what the button that we showed does is it looks for potential matching loops. So it finds long repeating patterns, long kind of chains of repeating instantiations of the same quantifier, and tries to generalize things for that chain of repeating instantiations. But even if it doesn't succeed in kind of generalizing it well, it will still try and show it and try and show some graph for it. But here we would be able to rule out those false positives and actually guarantee, guarantee that any matching loop that we find is a real matching loop. Or for instance, if we don't find any matching loops, then in the log file that you have, there was no behavior of matching loops. And the last slide that I have for future work is kind of a bit more broad. So this, this is something that is a bit more maybe into the future, but we actually also want to extend the tool to help debug other issues, not just with quantifiers. So another issue that can cause performance problems is if we have nonlinear arithmetic. So I could see kind of the tool helping you figure out where the issue that you're running into is. As well as some other visualizations of actually what the SMT solver is doing. So still the SMT solver is quite a black box kind of device. And so hopefully the tool could kind of let us peer into what is happening under the hood, what is kind of happening, where it's searching, and so on. And actually, I also want to call out that like, this is all interesting stuff that we clearly want to work on, but we're also very interested in kind of real world issues that people have. So I'm very interested in people getting in touch and letting me know, okay, I had this SMT file and it was being really slow, but I don't think it's quantifiers, or I don't think it's nonlinear arithmetic. And so I would like to take a look at and see kind of if there are any other issues that people run into when using SMT solvers. And so that's everything for the future work. And this is the final slide, where here I have a QR code linking to a repository which actually contains all of the examples that we saw today. So if you want to try it out yourself, maybe slightly change the examples or something, then you can follow this link, or you can scan the QR code. And on that web page, there's also a link to the tool itself, so to the repository of this Axiom Profiler 2.0. And yeah, that's kind of my whole presentation, and I want to open the floor to any questions that you might have.
I guess I'll kick things off. I have plenty of questions, but I'll ask a few to get started. First of all, thanks for the talk. I love the Axiom Profiler because it's really nice to see a sort of like proper engineering approach towards understanding SMT solvers, especially given that in the verification community, we tend to treat them really as black boxes. So I have a few questions. My first one is, in the examples you gave, you always seem to specify triggers manually, but many solvers have some sort of like model-based instantiations, like alternative strategies, rather than relying on user-provided triggers. Does the profiler work with those?
So it does work with those. I mean, if I open the last file that we saw actually here, where we kind of removed most of the instantiations that we had from the triggers. It's, for instance, doing here this model-based quantifier instantiation. And we do see those instantiations within the graph itself as well. It doesn't completely handle them because they will never have any parents, because it doesn't kind of somehow figure out what might have caused those. I mean, MBQI is a bit hard to to talk about. There will always kind of be a root node in the graph, but yeah, they do appear also in the graph.
Okay. So I guess that means that it's supported, but you can't really reason about matching loops, whatever that means in the context of MBQI.
Yeah.
Okay.
Yeah. But
Um,
again, yeah, I mean, I would be interested if people have issues where they run into MBQI causing some kind of matching loop or matching itself or something.
yeah. Uh, and then I also, I mean, at multiple points you referred to how the Axiom Profiler doesn't help you solve the issues it discovers, and you mentioned some papers that get into that. Have you thought about how possible it would be for the profiler to propose, like fixed triggers? Like, oh, I noticed that actually, like, sure, there's this trigger that causes a matching loop, but some percentage of the instantiations use this different trigger that doesn't seem to cause matching loops or something. I don't know.
Mm-hmm. Yeah, I think that's a very good point. Yeah. So I can definitely see it doing that. I think that would be possible. I think it's quite related actually to this point that I had about the future work where we use a kind of more formal approach. So I think if somehow the Axiom Profiler was able to build some internal model of exactly how this thing is being looped, and it could, for instance, use that model to extend it and show, okay, it would continue like this. So it really understood the matching loop very well. Then I think at that point, I mean, one very easy solution, for instance, would be to just try changing the trigger, right? You kind of fuzz it a bit and again, use your understanding of the semantics of matching loops and so on to simulate things and see, okay, would it still be a matching loop if I change the trigger like this? Maybe you could do actually something smarter, I'm not sure, but yeah, I think that is something that it could do. And it would also be nice for this other feature, right, where we're just it would be nice to have it. I mean, if we're really interested in how things are going under the hood, then we open it in this graph view, but otherwise we just throw it the file and it tells us everything, how to fix everything.
Yeah, I mean, that would be the dream, of course.
Yeah.
So I think Florian also had a question. He asked, do you think the action profiler could work with Z3's called via the API, e.g. directly from Camel? And also, does it support incremental SMT?
I can open the question as well. So it does work. So I'm not sure how it is when it's called through the API. I'm pretty sure that's fine. That like you can call it through the API and still specify that it should create a log file, and then while it's running, it will just log like write line by line to the log file. So I mean that's one thing that maybe is a bit important to mention is that this log file format is designed in a way that it can be cut off at any point. So what Z3 does is it just writes line by line and appends to it. And if we stop verification at some point, or even if we get a very big log file, then when I'm opening it in the tool, there's a cancel button where I can stop loading the log file at some point if I don't want to load all of it. And that works completely fine. So what Z3 will do is it will just output it line by line. And that will work even if you're doing it via API. And for the second part of the question, where whether it handles push and pop things, then yeah, currently the Axiom Profiler will, like that's logged within the log file if there's a push or a pop, and the Axiom Profiler handles it just fine. Maybe we could improve the visualization a bit. So currently there is no way to see what kind of if there was a push or a pop. So what might happen in such a situation is that, for instance, we have this term slot S index, and that might be introduced when in some kind of the stack frame in Z3, and then that stack frame might get popped, and then this term might be reintroduced again. And so what would happen is that within this graph view, we would have two nodes, which both corresponds to the same enode, or the enode, by that I mean term. So we would have two nodes which have the same term here, and people might get confused or might not understand why that is. If there is a push and then this and then a pop removes that term and then it gets reintroduced again, then this is not kind of somehow communicated in the graph. But otherwise, the tool is able to handle push and pop just fine. Yeah. Thank you. Any other questions?
I actually had one final question. If, of course, if somebody else has a question, I'd rather yield my time. But I was wondering, would it be interesting to sometime to effectively do a diff between two runs of a Z3 on some file, or perhaps two runs of Z3 on similar files? Would the Axiom profile, like, would it be possible for the Axiom profiler to help you figure out, like, oh, how did this change impact the instantiations of quantifier or something like that? I don't know if that's anything.
Yeah, that's like, yeah, that's also a nice solution actually, or a suggestion. We did actually, yeah, think about it a little bit. We haven't looked into it more, but yeah, I did imagine, or we imagined that we kind of hopefully maybe would be able to have somehow construct this graph for the two separate log files and compare the two graphs. And so I think if you took the two log files themselves and somehow tried to compare them, then that wouldn't work so well. Because it also depends on the order the things come in the log file. So then, but within the graph itself, I think you could find a correspondence between two nodes in the graphs and somehow compare the differences between the graphs. So yeah, I think that is a good suggestion. I didn't mention it in the future work, but yeah, that is something that we could definitely look at.
Okay, are there any other questions? I think if not, we might free Yonesh.
I would have one very simple one. How did you generate the Z3 files? Did you just manually type them in, like the ones that you showed in the example? Or did you convert them from Rust to Z3 first?
So this Z3 file here, you mean?
Yes.
So this one, yeah, I manually wrote it in. So these examples are taken from a paper so there is a paper on the old version or the old tool. So if I search this, then it's called the Axiom Profiler, Understanding Debugging, blah, blah. So there's this paper from 2017, I think, or 2019, which describes this old tool. And essentially, since the tools are quite similar, it will also quite well explain this new tool. And so they use some example which is very similar to the one that I used here today. So I kind of half changed it, typed it out a bit, and half took the example from what they have. I mean, generally, you wouldn't do this yourself. Like I started with this SMT2 examples, and for the demonstration purposes, I kind of essentially worked backwards and turned it into a Rust file so that it's way more understandable for a Rust audience. But generally, what I would imagine the workflow to be is that someone is developing a Rust verification tool, and then essentially what this Rust verification tool does is it takes Rust code like this and turns it into SMT2 files like this. So it's essentially a translation. And so then when you're developing such a tool, you would write some example Rust code like this. You would run your tool on it, get your SMT2 file with whatever axiom you've built in or whatever set of axioms that you've built into your verification tool. Then run Z3 on this SMT2 file, open that in the Axiom Profiler, and figure out, okay, have I done my translation, or with my verifier, the axioms that I put in by default, are those axioms good? Do they work well or not? So for instance, these axioms that I've written here in the Rust file with this injectivity and the next definition, I wouldn't really imagine those are something that appears within Rust, that, for instance, the user would write. This is something that I'm kind of imagining is built into the verifier. And even though the Rust file itself doesn't contain these axioms, I would imagine they end up anyway in the SMT2 files, and it kind of injects them to give Z3 some way to reason about the functions that it has.
Yeah, that makes sense. Thank you.
Mhm. Yeah, then I guess